My name is Sue Sanson, and I'm here to give you a short introduction to the paper on hydrodynamics of prey capture and transportation in choanoflagellates. So the first question is, of course, what are choanoflagellates? And choanoflagellates are microscopic unicellular filter feeders, pictured over here. They consist of a unicellular cell, a filter, which is where they capture bacteria that they then eat. And how they capture this bacteria is that they have this flagellar vein, which is constantly pumping water through these ribs and then basically capturing bacteria. Some of the choanoflagellates also construct this lorica, which is a dome-like structure, basically covering the organism. And the function of this lorica is still unknown, but we will look at it in this study as well. The choanoflagellates are important consumers of bacteria, which is one of the reasons why they're important, as in return, they generate inorganic nutrients for the growth of unicellular algae in seawater. They're also interesting because they have an ancestral relationship with animals, and many people try to study these organisms to understand the evolution of multicellularity. Next, let's look at the motivation for the study. There are still many unknowns about choanoflagellates, one of them being how does the feeding process work exactly? What happens after a bacteria is being trapped? How is it then moved down to the cell where it's being digested? In a recent study, they looked more closely at the flagellum and argued that its shape must be that of a sheet-like structure, also observed in other organisms. Otherwise, it simply cannot clear the volumes of water that we roughly know it clears. In this study, they also then subsequently looked at the flow around the filter and noticed that there are some interesting directional vectors that could suggest that the movement of prey down along the filter could be due to hydrodynamics. And that's what this study looks more into. So how do we do this? We split it up into two approaches, a static and a dynamic approach. In the static approach, we fixate prey. We vary the size and the shape of the prey. We place it in different positions around the filter, and then we look at the force evolvement during a beat cycle. And this gives us basically a basic confirmation or rejection on is there some force from the flow that could suggest an aiding transportation factor. Then in the dynamic approach, we let the prey freely drift as it does in real life. And we basically look, how does the static and dynamic approach compare? Do we see the same overall trends? We look at 4 different types of prey: small, medium, large, and elongated. Here pictured the medium-sized prey relative to the choanoflagellate. Then we consider 3 positions in the vertical direction of the filter. And then we consider 4 positions sort of around the circumference of the filter. So we split it into 2 planes, a plane parallel to the shape of the bead and a plane parallel to the width of the flagellum. And these 4 positions we name left, right, front, and back. So for the static approach, we ensure symmetry by modeling an entire beat cycle. We use Stokes' equation on the flow, and then we can find the forces on the prey from the flow. Then we do a bit of a hack by basically considering the resultant velocity of the prey using Stokes' law. So we fix the prey, but we artificially calculate roughly what their velocity would be from the forces. First, looking at the tangent forces, here we have the right-hand side prey in the beat plane and the backside prey in the vein plane, with and without lorica. From light to dark green, we have the bottom to the top position on the color vertically. What's interesting here is that we note for the middle and the top position, we actually have on average negative tangent force, which means this force points in the direction of the cell, which is the direction we want the prey to move in. Furthermore, we also note that there's The magnitude of the force in the bead plane is quite a bit bigger than in the vein plane. And it has been observed that these bacteria don't necessarily move straight down the collar, but also traverse multiple microvilli on their way down. So this could maybe suggest that there are certain positions around the collar that are more favorable in terms of prey transportation. Looking at the flow field in the bead plane, we see that at the max displacement of the flagellum, this vortex appears, which basically redirects the water downwards. And we see that the strength of this basically increases the closer you get to the center of this vortex. And that's also why we speculate that this downwards directed force is strongest on the top and in the middle of the collar, and not so much here towards the bottom, simply because you're too far away from this vortex to feel its effect. Looking at the vein plane over here, we here see along the edge of the flagellum two vortexes forming, which explains why prey in this plane, the force on those changes direction 4 times during a beat cycle. And looking over here at a horizontal plane cut through approximately the middle of the filter, we see with the flagellum being positioned here, a vortex forming along the edge also. And here we see this, the motion of the water could potentially be the reason why sometimes bacteria is observed to traverse horizontally from microvilli to microvilli. Here, looking at normal forces on prey, which are interesting because they describe how well hydrodynamics helps retaining prey that has been captured on the filter. And here we actually see that when normal forces are negative, that means hydrodynamics are actually pushing the prey away from the filter. And sometimes prey has been observed to actually escape captivity after being caught on the filter. So hydrodynamics could be a potential explanation for why that happens. You could also speculate that the reason why some of the choanoflagellates have a dome-like structure is because then if prey is lost, then it still is retained underneath the dome and can be then subsequently recaptured. From the simulated forces, we can take the average over a beat cycle and using Stokes' law get a rough first order estimate of the resultant prey velocities. And looking at without the Lorica, we see that in general for different types of prey sizes and shapes, in the middle and top part of the filter, we have a tangent velocity pointing down towards the cell. With Lorica, we only see this effect towards the top of the filter. Assuming this transportation velocity that we see towards the top of the filter would hold all the way down along the filter, then we actually get a transportation time from the collar top to the bottom, which is in the same order as has been observed in the real-life choanoflagellate S. rosetta. Now looking at the dynamic approach, we utilize the fact that the prey is torque and force free at any instance, since we have a Stokes flow. And this we can use to go through this iterative process of basically figuring out how do we obtain this condition with what prey velocity and rotation. Here in the end, we use the dynamic velocities to sort of validate the estimated velocities that we found from the static analysis. We look at both the normal velocities and the tangent velocities, and then we compare the static and the dynamic results. And what we generally see is that in terms of the sign or the direction of the velocities, we're in agreement between both the static and the dynamic study, but the static study seems to be overestimating the magnitude of the velocity by approximately a factor of 2. This we do expect based on sort of some of the rough estimates we've done using Stokes' law to calculate these velocities. In this comparison, we have shown for medium-sized prey positioned at different places on the collar. In conclusion, our results suggest that hydrodynamics do contribute to the transportability of prey in direction towards the cell at some positions on the collar, especially towards the top, but not at the bottom. And for that reason, our results doesn't indicate that hydrodynamics account for the majority of the transportability of prey. And rather, they suggest that hydrodynamics could be an aiding factor in the real means of transportation of prey, which we still do not know what is. We also found that when we remove the lorica, this area around the filter where prey are actually being pushed down towards the cell by hydrodynamics, that area extends when you remove the lorica. So it doesn't seem to be that the adaptive value of the lorica is related to the transportability of prey. Finally, the link to the full paper will be in the description box below.